Hello and welcome. In this video, we're going to take a little follow-up to our Frenet-Serre apparatus and maybe just analyze a little bit more the meaning of some of those little components. So we're going to take a look at a couple concepts in this video, and one is the osculating plane, which put simply is just the plane spanned by the unit tangent vector and the unit normal vector. Okay, so you get a plane. We'll see what that meaning of that is. And then we can also take a look at a little bit of an interpretation of curvature, which you might remember that curvature is inversely related to radius. And so the radius of the turn of the space curve, if it gets larger radius, you get less curvature. And if it's a smaller radius, you get more curvature. So let's start off just with a little recap of the Frenet-Serre apparatus first. And so by definition, we took a look at the tangent vector being the rate of change of our position vector r with respect to arc length. And then the normal vector, we get that by taking a look at how the unit tangent vector is changing. And because it's a unit vector, it never changes length, it just simply has a change in direction, and that would be in the direction of the normal vector. And then to get the Frenet-Serre frame, we take the cross product of the unit tangent and the unit normal to get the unit binormal vector. Well, curvature is the magnitude of the rate of change of this unit tangent vector. And then in order to get the torsion of our space curve, we got that from the rate of change of our binormal vector. Now, actually, if you want to, we can compact a lot of these formulas down into what we call the Frenet-Serre formulas. Now, first of all, we can write one of these equations for the unit normal vector as the rate of change of the unit tangent vector with respect to arc length is equal to curvature times the unit normal vector. We also have on the right-hand side here an interpretation of the rate of change of the unit binormal with respect to arc length. Well, what we don't really see here is a nice formula that gives us what the meaning of the rate of change of the unit normal vector is. But we can get that from definitions. We know that the rate of change of the unit normal is simply the rate of change of the cross product of B cross T. That's using the right-hand rule. Applying the product rule, and then plugging in our formulas for the rate of change of the unit binormal and the rate of change of the unit tangent here, we actually can find out that the derivative dn ds is equal to torsion in the direction of the unit binormal minus curvature in the direction of the unit tangent. Now, if you actually want a quick way to sort of memorize all of these definitions, we can write the system of these three differential equations in matrix form. Taking these three equations, we can see that the rate of change of our TNB, our Frenet frame, is equal to this 3x3 matrix in terms of curvature and torsion times our TNB Frenet-Serre frame. So that's a quick way of basically taking a look at all of the definitions of our Frenet-Serre apparatus and putting it into compact form. Now, of course, in reality, this is really just definitions of our Frenet frame, curvature, and torsion. We put all those definitions in terms of our parameter S as arc length. And it's not always possible to just take any space curve and easily parameterize that in terms of S. So remember, we do have maybe some more user-friendly formulas to calculate the full Frenet-Serre apparatus in terms of any parameter T. Here are those formulas. Now, the Frenet-Serre formulas are very nice and neat and compact when we write them in this matrix form, but in reality, it might be easier to calculate things this way, especially if we start off with R being the position of every point on our space curve. We let V be the derivative, in like velocity. We let A be the second derivative, in the case of acceleration. And if we omit the vector symbol, we just take that to mean the magnitude. Then we can use these formulas for our unit tangent, unit binormal, and unit normal, all in terms of T, and curvature and torsion as two scalar functions of T. With that little recap there, let's take a look at what the osculating plane means. And remember, this is the plane spanned by the unit tangent and the unit normal. Now, we'll have to assume that our curvature is non-zero. If curvature is equal to 0, then we can't actually define the unit normal and unit binormal vectors. But assuming that our function is not just a straight line, the osculating plane is the plane spanned by the unit tangent and unit normal vectors at any given point on our space curve. Now, it might help once again just remember that if the unit binormal is not changing, that means we have no torsion. That means that we have a planar curve. And that plane would be the osculating plane. So if we just have a circle, no matter what its orientation is, once we have a circle, it should exist on a plane, and it's just going to stay on that osculating plane. But the moment that we start turning that circle into something like a helix and we start having that twisting motion, our curve starts to leave the osculating plane. But that osculating plane just sort of kisses the curve. That's really where the name comes from. Osculating plane means kissing plane. It's just this plane that our function is grazing across, and if we have torsion, we will be twisting away from it. Now, once we've got the oscillating plane kind of in our mental image here, then what we can think about is how we interpret curvature on that plane. Well, assuming again that curvature is non-zero, using this inverse relationship, we will see that if we let rho equal 1 over our curvature, that is the radius of a circle in which we are sort of turning, the radius of curvature. And that gives us the idea of the circle of curvature. The circle of curvature, or if you want to call it the osculating circle, is the circle that lies in the osculating plane. Okay, so if our function was a planar curve, this would make a lot of sense. All of our curvature would just be on the osculating plane. So that's where our circle should be. It's in the osculating plane. Now the circle should be tangent to the space curve as well. So they are literally just kissing each other. The osculating circle sort of kisses this space curve. They share a single point in space and they both have the same tangent. And then we're going to make it have a radius rho equal 1 over kappa. Now what can be a little bit tricky, but using vectors, maybe not too bad, we can actually figure out what the center of this is. Now remember, if we even just start off with a basic planar curve, our space curve is curving towards the normal vector. So we want to find the center of the circle by taking a point on our space curve and heading in the direction of the normal vector. We just need to make sure we had the correct distance. Well, that would be 1 radius. So that gives us the equation to find the center of our osculating circle. And here I've drawn a little picture to kind of illustrate that. The position vector for the center of the circle, RC, would equal a point in the space curve, R, plus rho times n. N's a unit vector, so if we just want to head a distance of 1 radius in that, we just need to make a scalar multiple of n, of just rho. And so you can see here, I've got a point on my space curve indicated with the vector r, and then you see the tangent vector pointing where I'm going, the normal vector pointing in the direction of curvature. To get the center of the circle of curvature, I'm just going to head along n, scaled by 1 radius to get rho, and it will be the sum of 2 vectors, r plus rho times n. That'll give us the center of the circle. And just remember that since this lies in the same plane as spanned by t and n, then the unit binormal is actually a normal vector to both the osculating plane and this circle. Okay, that might be a lot to take in. It's hard to visualize that. So once again, let's take a look at Maple and let's see if we can try to visualize that in a way. Well, I've already prepared a little worksheet here, and there's a lot of commands going on. I'll take you a little rundown of how I made this worksheet and then take a look at an animation. So here I've got a couple important commands to let myself use things like cross products easily and norms easily and derivatives of vector functions. So I've got those included, and I've got my position function r of t as being a helix, just scaled so that it won't be completely huge with a very tiny Frenet frame when I graph it. And I've decided to just dip into negative t and positive t. Oh, one thing you'll notice about this helix, it's not a circular helix just of the normal form. You can see that our radius is increasing. So think about that. As you're heading up the z-axis, radius is increasing proportionally. It's a 1-to-1. Well, that would be a cone. So actually this is sort of like a helix that lies on a cone with both negative and positive values of t, so bottom and top half. I've got my Fresnel array frame calculated here, and I've got curvature. And the only reason why I have curvature calculated is so I can get rho, 1 over curvature. Okay, well, here's a couple new things. Plane. This is going to be the oscillating plane, and I've tried to make sure that it doesn't look terrible when I graph this. And what I've done is I've taken the unit binormal vector, and I'm dot product that with xyz minus position vector of any point on the space curve. So this, if I set that equal to 0 and solve for z, that's going to get me a function f of x, y that represents the plane. That makes it pretty easy to plot. Further down here with my plot 3D command, plotting the plane. And well, I had to mess around with this a little bit, but I'm basically making sure that I'm graphing it over an interval of x and an interval of y that should be pretty small. And the graphing interval for x and y follows the position of my function as I go around. Maybe don't worry about that too much. It's going to show up as purple and it's going to be semi-transparent. We'll see in a second. As far as the circle, if you were trying to think about how you make the equation of the osculating circle, you got to be a little clever here. We have the idea of the center of the circle being r of t plus rho times n. That's the center. Now you want to have this circle, well, you want this to rotate around that center, and you want it to maybe start, let's say I'm using a parameter u here since I don't want to conflict with t's. So letting my parameter be u, and well, when I wanted, let's say, to u equal 0, I want it to be the same point as what's on my curve. So by plugging in cosine of 0, this will end up equaling 1. Sine of 0 will equal 0. And you can see that I have the normal vector minus the normal vector. That means that my circle will start exactly at the same point as on the function. And as u increases, I wanted to travel in the same direction as the curve. So I've actually used a negative sign and positive sign so that the orientation of my circle matches the same sort of orientation as the space curve itself. Not super important, I guess. It'll just look like a circle. You won't be able to tell which way I'm going around the circle anyways. I'm plotting that down here. Space curve, circle, purple, and here we go. I've got 100 frames of animation. It might take a moment to calculate all of this. Lots of plots, all displayed at the same time, just to make a pretty little animation. Somewhat pretty. Let's just see. Make this as big as I can. You can see that it's a very bizarre curve. It does lie on a cone, though. If I look straight down, I have that circular motion. And here's my Fresnel array frame. The osculating plane as well is there. Maybe you can see how it's sort of just kissing the curve. And as I move forward, the radius of that circle is decreasing, and this osculating plane is always kissing the curve all the way through. And here's the idea of torsion. You can see how the osculating plane has the normal vector of that yellow vector. That is the unit binormal. And as the unit binormal changes, that's what we are talking about with torsion. It really changes quickly there. A lot of twisting around that middle point. So that is a lot of torsion. And then very little torsion, back closer to 0 as we get up here to the top as curvature increases again. So we can make this hopefully a fairly smooth animation here. You can see as it travels around, the circle of curvature is decreasing in radius, and it starts increasing in radius again. Thinking about torsion, we have very little torsion, very little twisting. The oscillating plane is mostly in the same orientation, and then it gets a lot of torsion as that oscillating plane twists, and then very little torsion as you see how that yellow vector doesn't change much. So I hope that gives you a little better visual representation of the Fresnel array apparatus. You can think about it where you can now see that circle, and if the radius is decreasing, you have more curvature. Curvature always being positive, could be equal to 0, I suppose. And then you've also got torsion. Now you actually see that plane, and as it twists around, you can really start to understand what that torsion means. So that's the whole pieces you put together. It gives you a good idea of how to describe a space curve. Well, thanks for watching. I'll see you in the next video.